Hi everyone, I'm Bhavik Chanda. I'm a master student at UC San Diego, and this is my joint work with Pracheta Sen from University of Liverpool. Our poster is titled A Counterfactual Explanation Framework for Retrieval Models. The motivation of our work comes from explainable information retrieval. Most explainable IR methods explain why a document was retrieved or why it was relevant to a particular query. But in our work, we study the opposite failure mode, which is a very important one, which is why was a potentially relevant document not retrieved. This matters in high stakes settings like legal case retrieval, patent search, in clinical information access, and financial search, where missing a relevant document can have serious consequences. The IR practitioners need a per document contrastive explanation for why a document was left outside the top K results. Our central research question is which terms, if added to a document, would improve its ranking under a given query and retrieval model. Formally, given a query Q, a retrieval model M, and a document D outside the top K results, our goal is to construct a counterfactual document D prime such that D prime is ranked higher than D. This explanation is the difference between D prime and D, which means the new words present in the counterfactual documents but absent from the original document. So our explanation is concrete. The document was missing because it lacked these terms. We call our method CFIR, or Counterfactual Framework for Information Retrieval. CFIR has two main components: a local top K classifier and a counterfactual document generator. We build a local classifier because retrieval models can vary differently internally. BM25 is a statistical lexical model, while DRMM, DSSM, etc. are neural or representation learning rankers. Instead of opening each model internally, CFIR builds a local approximation of model behavior for one query, which is Q. For that query and model, document inside top K are labeled class 1 and documents outside class K are labeled class 0. So the missed document is a class 0 document. So locally, retrieval becomes a binary classification problem, which is predicting whether a document is inside or outside top K. Each document is represented as a term frequency query feature vector. The vocabulary V is built from the important words in the retrieved document, not the full corpus vocabulary. And we use an importance function, impd, and we found out that birth representation based similarity between query and document uh, tokens work best for extracting all these important words. After training the local classifier, CFIR implies the counterfactual document generator CK, which creates candidate counterfactual vectors in the same vocabulary space as the original document. So the optimization function balances three goals. First is the Y loss term, which pushes the counterfactual towards the desired label, which means inside the top K. Second is the distance term, which keeps the counterfactual close to the original document so that the explanation remains specific to the missed document. Third is the diversity term, which encourages different counterfactual candidates to contain different added terms instead of collapsing to the same explanation. So our objective is simple: to make the document predicted as top K, keep edits minimum, and maintain diversity across explanation. We optimized this during using gradient descent. The key design choice that we did was an insertion and only constraint. CFIR only accepts a counterfactual vector which is d prime underscore vec if each coordinate is greater than or equal to the original document vector. Term frequency can increase, but it cannot decrease. So our framework does not delete or replace word, it only adds the missing words. This makes an explanation interpretable and practical. So now I will explain the evaluation metrics before I jumped on my results. The main metric we used was the fidelity score, or FD. Fidelity measures how often the explainable terms actually improve the rank of the document after being added. So FD tells us whether the explanation actually changed the retrieval output or not. The second metric is average new word, which tells us how many new words CFIR adds on average. The third one is the average query overlap, which measures how many added words are simply query words. This checks whether the document or like the method is doing more than just copying the missing query terms. So for our experiments, we evaluate on MS Markov passage, MS Markov documents, and TRAC robust. For each collection, we use 100 queries and select 5 documents which are not ranked in the top 10 for each query, giving 500 query document pairs per collection. And we test on 6 retrieval models, which are BM25, DRMM, DSSM, ColBERT, Mono-T5, and Split. Our main baselines are query word, which adds missing query terms, and top K prime, which adds important words from the already top ranked documents. We also compare with Prada and Credence, where Prada perturbs text to improve rank, while Credence is a sentence level counterfactual ranking explainer, which is adapted here in the reverse direction. In contrast, CFIR gives optimized insertion only term level explanations. Now here are the results. Across all retrieval models, CFIR outperforms query word and top K baselines in fidelity. This means that our proposed terms are more effective at improving rank rather than just simply adding query words or borrowing words from top ranked documents. Also, the strongest results that we got were on neural and representation learning rankers. So you can see on MS Markov passage, CFIR achieves 82% fidelity on Mono T5, 80% on Splade, and 75% for ColBERT. Overall, our counterfactual setup improves document ranking around 70% of the cases. The query overlap result is also important. The maximum query overlap we got was 68%. So CFIR is not simply copying query words. It often proposes terms which are semantically aligned with the list of documents and with what the retrieval model expected but did not find. This explains why CFIR worked well for models like ColBERT, Mono T5, and Splade, where these models uses richer semantic representation. So adding semantically useful words can strongly affect ranking. Our method exposes those missing semantic signals. So the main takeaway is that CFIR turns a retrieval failure into an actionable explanation. Instead of only saying this document was outside top K, our framework says this document was outside top K because it lacked these specific terms. This can help IR practitioners a lot to debug retrieval models, inspect model behavior, and identify systematic model preferences. The main limitation that we found is that CFIR uses a reduced vocabulary of important terms for computational efficiency, and for each query, we have to train a separate classifier. So to conclude, our works introduces CFIR, which is a model agnostic, insertion only counterfactual explanation framework for retrieval models. Thank you.